Okay, welcome to Chapter 10, Section 3. We're talking about inverse functions. That previous section ended with a kind of foreshadowing of what's coming with this. And that is that an inverse function undoes what the function does. So the big idea here is, and this works for looking at these situations algebraically or geometrically, is that we're interchanging. We're swapping the roles of x and y. So x in one becomes y in the other, and vice versa. Now, that looks fairly straightforward. It's just an interchange, a swap of x and y. Now, our goals for this section are to find the inverse of a function algebraically, to sketch the inverse of a function geometrically, and to use a new test, the horizontal line test, to determine if the function has an inverse that's also a function. So those are our goals. So let's take a look at this first example. Notice I haven't told you anything about these two functions, just that we've got a function and its inverse. So this first function, this first rule, is simply making an input into an output. So for example, it looks like this function f makes 0 into 1. If we put 0 into this function, out comes 1. 0 is the input, 1 is the output. Now, the inverse function is f inverse of x. So here's the notation for the inverse function. Now, it's not the inverse of g or of some other function, it's the inverse of f. So it will undo what f did. So for example, when we put 1 into f inverse, the inverse function of f, out will pop 0. In other words, whatever f does, f inverse undoes. So let's look at some more examples. Our function makes a 5 into a negative 14. The inverse function will take that negative 14 right back to 5. So if we put a negative 14 into the inverse function, out will pop a 5. Some of you have relatives like this. Whatever you do, they are excellent at undoing. One more numeric example. The function makes negative 3 into 10. The inverse function makes 10 into negative 3. It undoes what f did. In general, and this goes back to our big idea that the inverse function simply swaps x and y. If the function makes x into y, then the inverse function makes y into x. In other words, it makes it back into whatever you started with. Now let's talk about this algebraically. Now at first, when you look at this for the first time, that may look a little daunting. But that's basically saying f of f inverse of x. F of f inverse of x is x. Whatever f inverse did, f undid it. So whatever that input was, x, it's our output as well. These two functions undo each other. Whatever f inverse did to x, f undoes it. Now, here's a case where function composition is actually commutative. In other words, I can say the exact same thing for f and then f inverse. So this second example, f of x is being put into f inverse. So whatever f did to x, f inverse undid it. Our input was x, and after going through f and f inverse, our output is x. In other words, whatever one did, the other undid. Now, geometrically, this means that if we have a point, so think of this geometrically, think of AB as a point on the function. If I was graphing this function, I would see that the point AB is on the function f. So geometrically, that must mean that the point BA, that is when we swap the x and the y coordinates, is on the inverse function. So two things to illustrate that the big idea with an inverse function is that it swaps the role of x and y. Now let's talk about notation. I mean, by this point, hopefully when you see those parentheses, you're thinking to yourself, that's not multiplication, that's not a grouping symbol, that's not the base of an exponent. That is the argument, the input into our function. Now we're using some notation that we've seen before. There's an exponent, and the exponent is -1. And so you might be tempted to say, well, I know exactly what this is, except it isn't. This is not the reciprocal of f of x. In other words, it's not 1 over f of x. It's something much more unique to f, whatever that function is that we started with. It is the inverse of f of x. So that is our notation. We're recycling notation that meant something different before and now means the inverse. So conceptually, what we're doing when we find the inverse is what we had been doing all semester, and that is we're doing the inverse operation in the opposite order. So for example, if we have a function, in this case that function is y equals 3x plus 1, that tells us to do two things. It tells us to take the input x, multiply it by -3, and then add 1. Now, the inverse function is the inverse operation in the opposite order. And of course, we're swapping x's and y's. So our output y, what we get after multiplying by -3 and adding 1, is now our x. And then we're going to work backwards through the order of operations, undoing as we go. So where we had been adding 1, we're now going to be subtracting 1. Where we had been multiplying by -3, we'll now be dividing by -3. And also notice that the order has swapped. We're doing the inverse operation, but in the opposite order. If before we multiplied and then added, we are now subtracting and then dividing. So we're working in the opposite order. So take a look at this. It says that x, we start with x. The first thing that we do is subtract 1, so that's x minus 1, and then we divide by -3. We divide all of that difference by -3. So you can see exactly what that gives us. Here is our inverse function, x minus 1 over -3. So here's a function in its inverse, done using the methods that we've been talking about all semester. Okay, now we're going to look at the same question algebraically. We're going to find the inverse of this function. In the first example, it's -3x plus 1. We just did this using a kind of conceptual approach, just talking about the definition of algebra, that which undoes something, in this case a function, that undoes another function. So we've got a 4-step process here to do this algebraically. The first thing is to rename the function, whatever f of x, g of x, whatever function name we've given it, as y. So when we do that, we have y equals -3x plus 1. We're now going to swap x and y. The second step is actually when we find the inverse. We simply exchange the x and the y. So when x became a y and the y became an x. Now we're going to go through the process of solving for y. Remember, we know that we have a function if we can solve for y, if the y only appears once, and there's no plus or minus signs and only elementary functions. Well, the inverse of multiplication and the inverse of addition are certainly elementary functions. There's no need for a plus or minus sign. So let's go through and solve this. The first thing that I see is that we need to subtract 1 from both sides. So we're going to do that. We're going to subtract 1 from both sides. And then we're going to divide both sides by -3. So that's exactly what we got on the previous page. We're now going to do step 4. And step 4 says, give it that same function name, but now call it the inverse. So by working through these processes, especially by swapping x and y, we now have the inverse of f. So there's our inverse function, x minus 1 all over -3. Okay, let's work through another example, the same 4 steps. So the first thing we're going to do is make the f of x into a y. Then we're going to swap the x and the y. And then we're going to work backwards through the order of operations, undoing as we go. What does that mean? Well, it looks like 3 things happened to y. According to the order of operations, we subtract 5, we cube, and then we add 3. We're going to work backwards through that, undoing as we go. It looks like the last thing that the arithmetic tells us to do is to add 3. So we're going to undo that by subtracting 3 from both sides. So notice we've subtracted 3 from the right side. It's no longer over there. And we've subtracted 3 from the left side. The next thing, of course, is to undo the cube. We undo the cube with the cube root. So we take the cube root of both sides. And that gives us the y by itself. Now we can swap sides. That y equals could be on the left side. And when we do that, in our last step, we can rename that y f inverse. So f superscript -1. Now let's think about this geometrically just for a few seconds. Remember that when you find the inverse of a function, you're swapping x and y. So for example, if a point is on the function, the point AB, then the point BA is on the inverse of that function. So we're looking here at everything that stays put. So here's another usage of a dashed line, just a generic other line. Notice that we have 3 functions drawn, and we've got some points picked out. So for this first function, there's 3 points where the function crosses the diagonal, the main diagonal y equals x. And at those 3 places, the function is equal to its inverse. And the reason that that's true is because in those 3 places, on the dashed line y equals x, a equals b, so when we swap them, we get the same point. So there are our 3 points. We can be sure that they are on the inverse. We're asked to sketch the inverse function, and to do that, we're going to need some clues. And those 3 points on the dashed line and the function itself are also on the inverse function. There's another point here, and we can see that it is symmetrically arranged. In other words, if I fold it along that diagonal line, y equals x. So if I fold it along that diagonal line, y equals x, this point at x equals 2 would line up, would be on top of this other point. In other words, they're equidistant from the diagonal y equals x. So I know something else. I know that this other point is also on the inverse. Okay, so here's that graph in Geogebra. The green curve f is crossing the diagonal y equals x 3 times, and we can sketch the inverse of that. Notice that it goes through those same 3 points where the function crosses the main diagonal, and then that 4th point equidistant from the others. Okay, so here's our second function, shown in blue here, starting at 0, 0, and then crossing the main diagonal at 1, 1. This is actually half of the parabola. This is the positive branch for y equals x squared, and its inverse is the square root. So notice how in green we can see the inverse, symmetric about that diagonal, the dashed line there. Okay, and in our next example, we've got a line. It crosses the main diagonal at 1.5, 1.5. Its inverse crosses in the same place and has the inverse slope. We're going to end section 3 with an interesting observation, and that is shown in these 2 graphs. In the left side, we have a parabola. On the right side, we have its inverse. But notice that its inverse is not a function. It doesn't satisfy the vertical line test. So we're going to end section 3 with a question. And that is, how do we know when the inverse of a function is a function or not? Just because we have an inverse doesn't mean that it's going to be a function. So remember that the vertical line test tells us that this parabola is a function. So as we sweep this vertical line across the parabola, we see that for each input there's exactly 1 output. It tells us that this is in fact a function. However, when we find the inverse, we see equally well that the inverse is not a function. Now, it may be that the inverse is a function. We've seen an example of that on the previous page too. What we're asking here is if the inverse is a function. Now, take a look at what we're doing here. When we swap x and y, we're basically asking the question before we've made the inverse, is the inverse a function? So let's go backwards. Notice that this inverse is not a function because it does not satisfy the vertical line test. So you may then ask the question, well, what's the inverse of a vertical line? Well, the inverse of a vertical line is a horizontal line. So it looks like somewhere between 1 and 2, but closer to 2 than 1, are horizontal line on the inverse. So that is the same line. The vertical line on the inverse, the horizontal line on the function itself. Now notice that that horizontal line crosses the function twice. Now that doesn't tell us whether we've got a function or not. That tells us about the inverse. It tells us when a horizontal line crosses the curve more than once, it tells us that the inverse is not a function. So the horizontal line test tells us if the inverse is a function. If a horizontal line crosses a curve more than once, the inverse is not a function. The inverse still exists. We still have an inverse. It's just not a function.